In this video, I'm going to explain about that how to create the AVL binary search tree of a given element. So before going to the insertion operation and we can say that creation operation, first I will going to explain one shortcut trick that will be easy for you to understand that how you perform the LR rotation and RR rotation. LL rotation, there are 4 rotation you are performing. One is that LL and one is LR, another is RR and RA. Right, so these 4 rotation we were performing. That LL and RR is very easy. You are doing, doing that. Suppose you are getting that 66 and 65 and 64. So this is nothing but a LL rotation. So in LL rotation, what you are doing, you are performing right rotation and from the middle node. That's very easy. In the single step you are getting, right? For the RR, same thing you are doing. From the for RR situation, you are doing left rotation and from the middle node. That's very easy. But coming to the LR rotation and RR rotation, in this rotation bit complex, and that's also very easy, but bit sometimes people feel tough this part, but this is a very easy. But for that reason I'm giving the shortcut trick. So whenever you are theoretical performing example, means you are not going for the coding. For the coding part, this step is going to work. But for the shortcut trick, I'm going to just explain that for the understanding point of that for the example. So here I have a CAB. So this situation is nothing but a left and right rotation. So this is the RL problem. Sorry, LR problem. This is the LR problem. For that long-term method is that first we have perform here wherever the LR came, means first we have to perform the left rotation. First we perform the left rotation, then we'll perform the right rotation. So while performing the left rotation, we were performing between this A and B, means we always, one more thing is that do remember, whenever we are performing the rotation in the AVL tree, we always do perform between 3 nodes. So we always perform rotation between the 3 nodes. So whenever the LR situation will come, for that time first L rotation will perform, and that too what we will do from the last node to middle one. So this type of rotation will do that I have done it here. There I am performing left rotation. After performing left rotation, we'll get this one. After performing left rotation, we'll get this one, right? Then after first rotation done, 2 rotation we were performing here. For LR rotation, if we were doing 2 rotation, first left, then after we were performing the right rotation. So left rotation we were performing from the last node. Do remember that for the left rotation we were performing the last node, right? Then after we got it what, left LL. So for that situation, what we will do, we will perform the right rotation, and that too from the middle node. And after the performance, after the see this is the step, and after this we'll got that final one. We'll get the final tree, and that will be the balanced one. Right? So this is the long method. You have to perform 2 rotation, right? Similar like that for the RL. For the right left, for the RL situation, we will perform 2 rotation, and that too is what, first we will perform the right rotation, and then we will perform the left rotation. So this 2 rotation we will going to perform. So from the left rotation, if I am going to perform right rotation, if I am going to perform, then from the last node I will going to perform here. From the last node I am going to perform, and after this right rotation we got this tree. And here is that the situation is what, RR situation. So for that, from middle node I will going to perform that left rotation, and afterward we'll get this final tree, right? So this is a long way. Now I'm going to explain you the shortcut way. This is the one way you can do that. But shortcut way, if I'm saying that, suppose you are getting the LR situation. Suppose if we are getting the LR situation, and this is your tree. This is the C, and L, left is A, and right will be the B. So this situation is nothing but a LR. So for that situation, what will be the shortcut way? The shortcut method is that whatever the last element, make it root. whatever the last element, that will become the root, and their parent will become the left children, and the other one is become the right children. So this will be the LR. Similar like that RL. RL, what will you do? RL situation is that A, C and B. For that situation, what we will do? Whatever the last element, just make it the root node. So B become the root and B become the root and C become the right side. C is a, here we were performing our what? RL. So C is become the right children, or A is become the left children. So this is the shortcut method. Whatever the last node, that will become the root. And remaining variable you have to accordingly arrange. So this is the shortcut method. And this is the long cut method. So I have explained both method. Whatever you feel comfortable, try to use that one. Okay. Now I'm going to create the AVL binary search tree of a given element. So I have some given element is 26, 21, like that. This given array is given. Now I'm going to insert each and every element for the constructing the AVL tree, and we already know that AVL is the balanced binary search tree. Means for maintaining the balance, we were calculating the balance factor from height of the left children minus height of the right children. That will be the balance factor that we were going to calculate for each and every node. So now I'm going to insert 21. So first I'm inserting the 21. First I have inserted 21. Then after I have calculated the balance factor. So balance factor of the 21 is what? There is no left children, no right children. So it will be 0 minus 0. It will be 0. So this is balanced. And one more thing is that the node balance factor range should be 0, minus 1 and 1. Do remember this one. Each and every node balance factor in the range of 0, minus 1 and 1, then we can say that it's balanced. If it is not in that range, we can say that it's not balanced. Then after we will perform the rotation. Right? So 26 come. For the 26, I will going to check from the root, because here AVL tree is a binary search tree. So 26 come, will check that is 26 less than 21 or greater than. If it is less than, will be insert in the left part. If it is greater than, will insert in the right part. So here 26 is the greater, so I have inserted in the right part. Right? I have inserted. Insertion done. Now we'll calculate the balance factor. So if I calculate the balance factor of the 26, that will be 0. Why so? Because there is a no left and there is a no right. So their balance factor will be 0. For 21, there is no left children but right children we have. So what is the balance factor for this one? 0 minus 1. That will be left children is no left children. So 0 minus 1, that will be the minus 1. Right? So that will be the minus 1. So 21 balance factor is minus 1. Right? Now coming to the 30. Now I'm going to insert 30. So while inserting the 30, I will start from the 21. Is 30 is less than 21 or greater than? So it's greater than. I'll come to the right part. Is 30 is less than 26 or greater than 26? So it's greater than. So 30 will insert it in the right side. Now I'm going to calculate the balance factor. Balance factor of the 30 is 0. Balance factor for the 21 is 1. Balance factor for 21 is there is a no left children. So that will be 0 minus what is the height of the right subtree? Right subtree is 2. So 0 minus 2 will get it minus 2. Now check that is this balance factor of each and every node. 30 is balance factor 0. That's in the range of this one. Yes, true. 26 balance factor 1. 1 is in the range of this one. Yes. But what if 21 balance factor? Balance factor of 21 not coming in this range. So it means that this tree is not balanced. Then performing that, we'll perform the rotation. We'll see that what type of rotation it is, right? So first step, I have inserted element. First step, I'm inserting the element. Second step, what I am doing, I'm calculating the balance factor from the last inserted element to root node. Do remember, I am calculating balance factor from the last inserted elements. 30 I have inserted. From there to root node I will going to calculate balance factor, and wherever in between from new node to root node, if it is in between a node violating the balance factor property, means they are not coming in the range, there we stop and check that what type of the rotation will be performed. So suppose here from 30 to 21 I raise, and here balance factor is violating, it's not coming in the range. Now from that node onwards, wherever the violation occur, from that node onwards will go check that what type of the rotation it is, what type of the rotation it is. From upper to down will violated where 21, right? From there onwards I will go and go to the that direction, wherever the inserted node, in that direction will check that what type of rotation it is. So it is nothing but a RR, it is nothing but a RR rotation, right? So if it is the RR rotation, for that what will you do? You have to perform right rotation, sorry left it's RR na, then we will going to perform left rotation, sorry here we will going to perform left rotation, we'll perform the left rotation, and that too from middle, we will going to perform left rotation, and that too from the middle element. Do remember, always perform the left rotation and from the middle one. So if I calculate, mid will be 26 will become the root, and 20 will become 21, because performing left means 21 come down, 21 come down, so that will become the left children, and 30 is right children only. So after the rotation we got this final tree, and now we'll calculate each and every node balance factor. Still is there any node that's violating the AVL property? If it is still violating the property, again we'll perform the rotation. So it's not mandatory that if I'm going to insert the element, it means that only one rotation is going to perform and you will get that balance one. No, this is not possible. Sometimes you will going to perform twice, thrice, 4 times also you will get. Suppose if it is you have a big number of data, and for that situation if you are using AVL tree for maintaining the height balance, sometimes many time rotation you are going to perform. Even after this rotation you will get sometimes again violating the AVL tree property, then again you perform the rotation. So step you have to, this rotation you have to continue until unless you will get the balanced AVL tree. So now I have calculated the balance factor for every node, and I have seen that all this is in the range of 0, -1 and 1. Next element is 9. Next element 9 I am going to insert. So first I will check that is 9 less than 26 or greater than. So it's less than, I will come to the left part. Here I will check that is 9 less than 21 or greater than. So it's less than, I will insert in the left children of the 21. So 9 I have inserted. Now first step is done, insertion done. Now next step what we will do, we will start from the 9 to root node balance factor. We will calculate balance factor from 9 to root node, right? So 9th balance factor is 0, 21 balance factor is 1, 26 balance factor is 1. So here we have seen that till root node there will be no violation. Then after we'll calculate the other node balance factor also. If it is there is no violation in the path, then after we'll calculate the other node balance factor also. If it is not, if it is all the balance factor is coming in the range 0, -1 and 1, it means that this tree is balanced. Now the next, see this tree is my balance. So now I'm going to insert the another node. Now I'm going to insert 4. Now I'm going to insert 4. So for 4 what we will do, again we'll check from the 26, is 4 is less than 26 or greater than. So 4 is less than, so I'll come to the left. Is 4 is less than 21 or greater than, so it's less than, so I'll come to the left part. I'll check here again, is 4 less than 9 or greater than 9. So it's less than, so I will going to insert 4 in the left children. So left children of 9 is 4, I have inserted. Now insertion done. Now next step what will we do, I will start calculating balance factor from the 4 to root node, right? We will start calculating balance factor from 4 to root node. So 4 balance factor, if I calculate balance factor of the 4, we will get that 0, because there is a no left children and there is no right children, so there is 0. For 9 balance factor you will calculate, you will get it 1. For 21 you will get the balance factor is 2. Now you stop here. You stop here. Not required to calculate the balance factor of 26 and 30. You stop there because here only violation occur. Because the height of the left children is 2 and right children is 0. So 2 minus 0 you will get it what? 2. 2 you will get. So here is the violation occur. So what will you do here? Here violation occur, then what will you perform here? Then you check that violation occur at where? 21. So from 21 onwards, onwards you start checking that which type of the problem occur, means which type of the rotation is it is, right? So what will you do? Check that what type of it is. It is LL. It is nothing but a LL. So if it is LL, I have already explained in the previous video. If it is LL, then what will you do? You have to perform right rotation, and that too from where? Middle. That too from where? Middle. You perform middle node. So 9 will become the root, 21 will become the right children, and 4 is the left children. So after this you will get it there. After the performing the rotation you will get this string, right? Remaining you have to simply add. So now you have to see that 26 left children is 21, but 21 is the right children of the 9. Then you have to, what you have to do? You have to 26 is added with the 9 and 30 will be as it is. So you have to, this remaining part will be as it is. You have to simply add it. So afterward you calculate the balance factor of all these nodes, and now check that is there still any violation. So there is no violation here. Each and every node balance factor coming in the range between 0, -1 and 1. So this is balanced now. Now I'm going to insert the another element. So now I'm going to insert the 14. So when inserting the 14, again we'll follow the binary search procedure, binary search tree insertion procedure. 14 is less than 26 or greater than, less than, come to the left part. Is 14 less than 9 or greater than? So greater than, so I will come to the right part. Is 14 is less than 21 or greater than? So it's less than, so I will going to insert in the left part. 14 is inserted. 14 is inserted in the left children of the 21. Afterward, now I will going to calculate the balance factor from 14 to 26. Right? I will start calculating balance factor from 14 to 26. If there will be no violation, then we'll calculate the other node balance factor. If it is the violation occur, we'll stop there and start performing the rotation, right? So from 14 I have calculated the balance factor, that is the no left no right, so the balance factor will be 0. For 20 and 21 balance factor is 1. For 9 balance factor is -1. So with 26, now calculate the 26 balance factor. So balance factor of 26 is what? The height is here 3 minus 1. 3 minus 1 is 2, because this height is 3 minus 2. So here is violating the property. At 26 it's violating the property. Then after, what will you do? This tree is not balanced. Then what will you do? So for this situation, mostly people will confused here. So in this situation, what will you do? You start violation occur at which place? At 26th node. Violation occur at 26th node. So what will you do? From that node onwards, from this node onwards, start checking what type of the violation it is. And one more thing, one is that you start from the checking from the node their violation occurs. So 26 you start from here. Now you will check that here LL. But one more thing, don't go to this 4. Don't say that this is the LL. No, not at all. Don't say that. Why so? Wherever the last node you have inserted, the last node you have inserted, from that direction you go. So your last node inserted is 40. Because of this 14, your tree is violating the AVL tree property, right? So from that direction you go. So this is the left and this is the right. You only take the three node only for the rotation. Don't go with this. Okay, because I've already explained the previous video, only you have to perform with rotation between the three node, right? And that too from the last inserted node. 14 is inserted now, so you have to check from 26 to 14 side, not to 4 side. Don't go with go that side. So this is left and right problem. So this is LR problem. This is LR problem. So for LR problem, what will you do? For the long cut method, you have to perform left rotation and then you perform right rotation. Long cut method, right? So for long cut method, you have to perform from. So you will get it here. What was the problem here? Is getting that 26 and left side is 9 and right is 29. So this is you have a this is the concept, and here is the LR. And if you go with the long cut method, so you are performing what? Left rotation, and that too from what? Last node. So here you perform left rotation. So afterward what will you get? 21 will come with root, right? 21 came up and 9 will goes down, and 26 is their own place. 26 is still there. So this is the one rotation I have done. Now we have a perform right rotation. So which rotation it is? It is LL. It is LL. So for this one, what do you perform? Right rotation. So from middle onwards. If you perform the middle onwards, you will get it what? 21 will come up and 26 will goes right side and 9 will come to the left side. So this is what? This is the long cut method. This is the long cut method. But now I am going to explain you the shortcut method. So shortcut method, what will you do? Directly 21 will become the root. 21, whatever the last node, that will become the root. And 9 is become the left children and 26 is with the right children. Whatever the last element, that will become the root, and we are performing what? RL. So this 9 become the left side and 26 become the right side. So after this we got this tree. After the performing rotation, final rotation, we got this. Now remaining part you have to insert as it is, and now you will get confusion sometimes how to insert. So after the rotation you got this tree. Now you have to insert what? 4, 30 and 14, right? So 30, where 30 is going to insert? 30 is the right children of the 26. So where is the 26? So right children of the 30 is inserted. Okay. 4 is the left children of the 9. 4 is the left children of the 9. So you have to add it. Now coming to the 14. 14 is the right children of the 21. 14 is the left children of the 21. 14 is the left children of 21. So 21 left children is 9. That's already filled. There is no place. So 14 will going to insert to the right children of 9. So there 14 is inserted. Okay. Now calculate each and every node balance factor. If you calculate balance factor of each and every node, you will see here 4 balance factor is 0, 14th balance factor is 0, 13th balance factor is 0, 26 balance factor is -1, 9 balance factor 0, 21 balance factor is 0. So all these are in the range of 0, -1 and 1. So this is balanced. Now we have a final tree is this one. Now I am going to insert what? 28. Here I am going to insert 28. So when inserting the 28, how will you insert? Again we'll follow the binary search tree insertion procedure. 28 is less than 21 or greater than? It's greater than. I will come to the right part. Is 28 is less than 26 or greater than? So greater than, I will come to the right part. Is 28 is less than 30 or greater than? So it's a less than 30, then 28 is going to insert in the left children of 30. So 28 is inserted. Now what we will going to do? We will going to start calculating balance factor from 28 to 21. Right? In between, if it is the violation occur, will stop there. So I will calculate the balance factor of 28, that's 0. Balance factor of 30, that's 1. Balance factor of 26, that's 2. The balance factor of the 26, you will get it 2. Why so? Because there is a no left children, but right children is having height is 2. So it's a -2, it's a -2, you will get it the -2, 0 minus 0 minus 2, you will get it -2. So here this is going to violate 26 is sorry, here it's violating the property, then not required to calculate the balance factor of 21. Now check, violation occur at what, where, 26. So from that node onwards, 3 node you have to check that what type of the problem it is. So first is L and this is R. Oh sorry, this is R and this is L. So what situation it is? RL situation. What situation it is? RL situation. So if you go with the long cut method, RL, name is saying that RL means R means first left rotation, then L means left, right, for R means first right rotation and then left rotation. So whatever the name is saying, that rotation we will going to perform. Don't confuse with that, right? So here is that RL you are getting. So you have to perform first right rotation, then you perform the left rotation, right? So that is the long cut method, but here I am going to go with the shortcut method. So I just make the 28 is the root. So first I have made that 28 is the root, and 28 is the root, and 30 become with the right children, and 26 is become the left children. Okay, this is a shortcut method. If I go with the long cut method, what will we do? First we will perform the right rotation, and that from the last node. If I perform the right rotation from the last node, so 28 become first and 30 will come to the right rotation. I am performing the right rotation so 30 will come to the right side. Right rotation from performing from the 28, so 30 will come right side, and 26 will come the 26 is as it is. 26 is as it is. So which situation it is? The situation is nothing but a RR. And for RR situation, what will you perform? You have to perform left rotation, and that too from middle. That too from the middle. So afterward, what will you get? That 28 will become root. 26 will come down, and 30 will goes to the right part. So after this is the long cut method, and this is the short cut method. Okay. So this I have done. Now I have to insert all these remaining trees. So that's remaining is almost similar. So simply have to add it all this, and then after calculate the balance factor. If you calculate the balance factor of each and every node that's come in the range, then it's fine. If it is not come in the range, then we perform again rotation. But here balance factor of each and every node is coming in the range, so it's balanced. Now I'm going to insert another element. So my another element is 18. Now I'm going to insert 18. So for the 18, same procedure I will do. I will check from the root, is 18 less than 21 or greater than. So here 18 is less than, so come to the left part. Is 18 is less than 9 or greater than? So it's 18 is the greater than, so come to the right part. Is 18 is less than 14 or greater than? So for 18 is greater than, so 18 is inserted. Now I am going to calculate balance factor from the 18 to 21. So I have calculated balance factor for 18 is 0, for 14 is -1, for 19 is -1, for 21 is 1. It means that this path all node is balanced. Now we'll calculate the other node balance factor also. Is my other node also coming in the range? Then we say that it's balanced. If it is not coming in that range, we say that not balanced, and we'll perform the rotation, right? Now here is all this balance factor, all this node balance factor is coming in the range, then it's fine. If it is not, if it will not come, then we'll perform the rotation. But here all these are in the range, so it's fine. Now I'm going to insert another element, that's 15. Now I'm going to insert 15. So for 15 again we'll check that is 15 is less than 21 or greater than. So it's less than, I'll come to the left part. Is 15 is less than 9 or greater than? So greater than, so I'll come to the right part. Is 15 is less than 18 or greater than? So it's a less than, so I will insert in the left part. Now after the insertion, I will calculate the balance factor from the 15 to root, right? So I calculate the balance factor of the 15, that's getting 0. 18th balance factor is 1. 14 balance factor is -2. And 9 balance factor is 2. But here is a violation occur. At 14 is violation occur. So we will going to stop here. At 14 is violation occur. We're going to stop here and we'll check that what type of the violation it is, what type of the rotation it is. So it is nothing but a R and L. This is nothing but a RL. So for this situation, what we will going to do? Perform first right rotation. First we have to perform right rotation, then perform the left rotation. And for right rotation, from where we have to perform? From the last node, 15 to 18. So right means, see that 15, I am taking 15 and putting it up, and 18 is coming down. So like that you are getting that 15 come up, 18 will come to the right part, and 14 is still there. This situation you will get that, right? And this situation, if you see that this is the right. So for that region, what you have to perform now? Perform left rotation, and that too from middle. Left rotation means you have to take 15 and come to the left part, right? So 15 will goes up and 14 come down. So afterward, what will you get? 15 will come here, 14 come down, and 18 will is as it is. 18 is as it is. So after the rotation, after the RL rotation, you will get it what? You will get it this one. You will get it this one, right? Now we have to insert the remaining tree. You have to insert the remaining tree. So 9 right children was 14. 9 right children was but 14. So 14 is already in left children of the 15. So 9 is 9. Now 9 right children become the 15, right? And remaining as it is, you have to simply merge, right? So after the insertion of the 15, you got this one. Now you calculate each and every node balance factor and check that is it coming in the range of 0, -1 and 1. If it is all the balance factors, you have calculated balance factor 0, 9, 1, 21, 1, 28, 0, 30, 0, 0, 26 is 0, means all these are coming in the range. It means that this is the balanced. Now I'm going to insert element is 10. Now I'm going to insert element 10. Same procedure, first step, is 10 less than 21 or greater than 21. If it is less than, we have to go to the left part. So here 10 is the lesser than, so left part. Now is 10 less than 9 or greater than? So 10 is less than 9, greater than 9, so I'll come to the right part. Is 10 is less than 15 or greater than? So 10 is less than 15, so I'll come to the left part. Is 10 is less than 14 or greater than 14? So it's less than, I'll come insert it in the left part of the 14. So I have inserted. Now I have inserted. Now I will going to calculate what? Balance factor. Now I am going to calculate balance factor from 10 to root node, and root is what? 21, right? So I am going to calculate balance factor from 10 to 21. If it is in between violation occur, we'll stop there, right? So I have calculated 10 balance factor 0, 14 balance factor 1, 15 balance factor is 3 minus 1, sorry 2 minus 1, that's 1, and 9th balance factor is -2. So here the violation occur. Here the violation occur. So wherever the violation occur, from that node onwards, 3 node, and the direction is the last inserted node. Last inserted node is 10. I will not go to the 9 to 18. I will go to the 9 to 10th direction. On that basis, you calculate what type of the rotation. So 9 to 15, it is what it is? It is left. What it is? It is, sorry, it is right. It is right. And 15 to 14 is left. So what type of problem it is? It is a problem of RL. It is a problem of RL. So first what we will perform? We have to perform right rotation, then we perform left rotation, right? So don't confuse that why left and right. So left means that you come to the left side, and right means come to the right side. But here is, what is that? Here you have to perform rotation between 9, 15 and 14 only. You have to perform rotation between 9, 15 and what is that? 14. In this 3 node you have to perform rotation, and that too is what? R and L. So first you have to perform what? Right rotation, and right rotation from what? Last node. Last node. So you have to take 14 and come to the right side. Come to the right side. So 14 will goes up and 15 will come down. So 14 goes up and 15 come down, and that too in the left side, and 9 is as it is. Put it as it is. So what is this situation now? R. So next rotation, what you have performed? Next rotation you have performed left, and that too from middle node. That too from the middle node. So 14 goes up and 9 will come down. So 9 is come down, 14 goes up, and 15 is as it is. 15 is as it is. So after this rotation, you got it. What tree? You will got that. Which tree? This one. This tree you got it. Right? Remaining now we have to add. Where was the 10? 10 was the left children of the 14. 10 was the left children of the 14. So 14 left children is 15. Sorry, right children 15, but left children is 9 already filled. So 10 will become the right children of 9. So 10 is become the right children of the 9. 4 is the left children of 9. So 4 is directly added. Now remaining part, right? So 29 left children was 9. So 9 is already left children of the 14. So 14 is become the left children of the 21, and remaining you have to simply add. So you got this tree, right? You got this tree. Now calculate the balance factor of each and every node and check that is it balanced or not. If it is balanced, okay, no problem. If it is not balanced, check that what type of the rotation will you going to perform. So we'll get that balanced one. So here all these nodes are balanced, so not an issue. So this is already balanced. Now I'm going to insert element 2. Now I'm going to insert 2 here. So again procedure is same insertion procedure. From 21 is 2 less than or greater than, less than, come to the here. For is 2 less than 14 or greater than, yes, less than, yes, is 2 less than 9 or greater than. So 2 is less than 9. So come to the left part. Is 2 less than 4 or greater than? So it's less than, so you have to insert in the left part of the 4. I have inserted, right? Now start checking from where? From 2 to root node. And wherever the violation occur, stop there. So violation occur at root node, where we have to calculate balance factor for 2, for 4, 9 and 14 and the 21. You got that by violating the property at 21. Right? Now you have to start checking that what type of the problem it is. What type of the problem it is. And that to start from where? From 21 onwards. That too have to start from where? From 21 onwards. Right? So I am going to start from the 21 onwards and will check that what of the problem it is. And the direction will be the last element that I have inserted. I have inserted what? 2 I have inserted. So for that direction will take. So violation occur at 21. From 21 onwards, check that which children it is? Left children. And then after this is also left children. This is also the left children, right? So we will going to take here which rotation we will perform. Where we will perform the right rotation. We will going to perform right rotation, and that too from the middle node. Middle is what? 14. So what we will going to get that 14 become root, and 21 become the right children, and 9 is become my left children, right? So I have performed rotation between 21, 14 and 9, and this is the LL situation. So we will perform the right rotation, and after the rotation we got this one. Now simply you add the remaining tree, right? So 4 is the left children of the 9. So okay, you added 4 here, and 4 left children is 2, that also added. 4 right children is 10, so 10 is also added, right? Remaining is 15 and 18, where 15 and 18 is going to insert. So 15 is the right children of the 14. So right children 21 is already filled, so they are left children. So 15 is become the left children of 21, and 18 is the right children of the 21. So this is added here. Now coming to the 21, where 21 is going to insert it. So 21 left children is 14. So okay, that 14, sorry, not 21. This is not a 21. 21 is already inserted here. Now is we have to insert this part, 28, 26 and 30, way to insert that, right? So 28 and 26 and 30 is the right children of 21. So you have to insert here here is free. So right 21 right children is now 28, and 28 is left children 26, and right children is 30. Afterward you got this tree. This is the final tree. This is the final tree. Now you got the final tree. Now you have to check balance factor of each and every node. After that, inserting element 2 and performing the rotation, still your tree is balanced or not. So for that reason, you calculate balance factor of each and every node and check that it is coming in the range of 0, -1 and 1. If it isn't coming in the range, then it's fine. If it is not coming in the range, again perform the rotation. Here is all these are coming in the range, it means that all these are balanced. So this is all about the insertion, and we can say that the creation of the AVL binary search tree. The time complexity of this is nothing but a order of log n. The time complexity of a AVL tree insertion operation is order of log n. That's all about this insertion operation. Thank you for watching my video.